Okay, if you're an engineer, you know this feeling all too well. You kick off a training run, you're watching the loss, and it just flatlines. Or maybe it's bouncing all over the place, never actually converging. It is one of the most frustrating things in machine learning, right? But what if that instability isn't just random bad luck? What if it's actually a predictable feature of the training landscape? Well, new research is giving us a much clearer map to navigate this stuff, and it reveals a really powerful way to get stable, reliable convergence almost every time.
So, for decades, really, our map for training models was guided by one core idea, that classic trade-off between bias and variance. This simple balance basically dictated everything we thought we knew about model size and complexity. And this U-shaped curve, that was the map. It was the whole playbook. On the left, you've got your simple models that are underfitting. On the right, your super complex models that are overfitting. And for years, the goal was always to find that perfect, magical sweet spot right there at the bottom of the U. This was just conventional wisdom. But then came these massive modern neural networks. Models with billions of parameters that can perfectly memorize the entire training set. And yet, somehow, they still manage to generalize incredibly well. I mean, these models live way, way out on the right side of that U-shaped curve, and they are breaking all the old rules. This is the new map. This is the double descent phenomenon. It shows that right after the test error peaks at that classic overfitting point, something really weird happens. If you just keep making the model bigger, the error starts to go down again. This just completely blows up our old understanding and suggests that the world of these huge overparameterized models, well, it operates under a totally different set of rules. So, to really get why this happens, we need a new metaphor. Forget a simple 2D curve. I want you to picture a lost landscape, a totally mind-bending, high-dimensional space. Your optimizer? It's like a tiny hiker trying to find the absolute lowest valley in this enormous, treacherous mountain range. And believe me, this landscape is incredibly weird.
And one of the weirdest and most important features in this landscape is something called a saddle point. So imagine you're standing in a mountain pass, right? In front of you and behind you, the path goes up, but to your left and your right, it slopes down. That's a saddle point. Now, for an optimization algorithm, this is a super confusing place to be. The gradient is almost zero, so it has no idea which way is actually down. And here's the key finding from the research. In what's called the mildly overparameterized regime, where your model is just a little bit bigger than it needs to be, the landscape is absolutely littered with these saddle points. This creates an incredibly rough and difficult terrain, and it's one of the main reasons why training runs in this zone are so unstable and just fail so often.
So the challenge then isn't just about the landscape itself. It's about how our training algorithm actually moves through it. The dynamics of that movement are what determine whether we get hopelessly stuck or find a clear path down to a good solution.
So in those narrower, mildly overparameterized models, the optimizer hits that dreaded plateau. It gets close to a saddle, the gradient just vanishes, and your training grinds to a halt. You're completely stuck. But in much wider networks, something incredible happens. The algorithm doesn't get trapped. It develops this beautiful saddle-to-saddle flow, where it's almost surfing from one saddle to the next, never really slowing down and always making progress. Okay, so we've diagnosed the problem, a rough landscape full of these tricky saddle points. Now for the fun part, the solution. How do we, as engineers, make sure our optimizer finds that smooth, saddle-to-saddle flow and just works? This table breaks it down really nicely. The underparameterized regime, it's full of traps. The mildly overparameterized regime, that's the danger zone we've been talking about, dominated by that roughness from all the saddles, which makes training totally unreliable. But look at the last one, the vastly overparameterized regime. Here, the influence of saddles is low. They're super easy to escape, and convergence becomes highly reliable. And if you need proof, just look at this graph. It's so clear. The blue lines are the training runs for those mildly overparameterized models. You can see how the loss just fails to decrease. They're getting stuck. But the red lines, those are the vastly overparameterized models. It's a completely different story. They consistently and reliably converge to a zero-loss solution. This is the big takeaway. Overparameterization isn't the problem, it's the solution.
So the obvious question is, how much is vastly? Thankfully, the research gives us a really clear, actionable rule of thumb. To make sure you're in that smooth, stable training regime,
You want to aim for a model that is at least 2 to 4 times more over-parameterized than whatever the minimum required size is. That's what gives the optimizer enough space to navigate around all those rough patches. Now, beyond just making your model bigger, there are a few other powerful tools for your toolkit. Using a learning rate scheduler is absolutely crucial. Experiments actually show it can get rid of that problematic double descent peak and just smooth everything out. It's also smart to limit your training epochs, because even these giant models can eventually overfit if you just let them run forever. And finally, adding a little bit of noise to your gradients, think of it like a helpful nudge that can push the optimizer out of a saddle it might otherwise get stuck in. So let's say you do all this. You navigate the landscape perfectly. What does the final model actually look like on the inside? Well, the payoff isn't just a low error score. What happens is the emergence of this incredibly elegant and efficient internal structure. And this destination has a name. It's called neural collapse. In the final stages of a good training run, two amazing things happen. First, the internal features for all examples of the same class, like, say, every single picture of a cat you showed it, they all collapse down to a single point. And second, these points for each class arrange themselves into a perfectly symmetrical, maximally separated structure. This is the signature of a model that has found the most robust and efficient solution possible. This all leads to a really profound shift in how we should think about what training even is. As one researcher put it, with over-parameterization, we are providing a search space that is so vast that the functional logic can be found rather than just learned. The training process becomes less about teaching the network from scratch and more about just finding a solution that was kind of already there. And that leaves us with a pretty fascinating thought to end on. This idea connects directly to other big concepts like the lottery ticket hypothesis, which suggests that these huge networks might actually contain smaller, perfect subnetworks right from the start. So the next time you scale up your model to make training more stable, just remember, you're not just adding complexity. You might just be giving your optimizer a better chance to find the elegant solution that was already hiding there in plain sight.